I want to start with a number today. It is a big one, so stay with me here.
Let's hear it.
299,792,458.
Ah, I know that way.
You definitely do. That's the exact speed of light in meters per second.
The cosmic speed limit.
Right. The absolute hard ceiling of the universe. Nothing with mass goes faster.
And it's a number that, physics students basically memorize right alongside pi.
Exactly. But knowing the number is the easy part.
Oh, yeah. Understanding what the universe actually looks like when you're moving that fast, that is where things get really messy.
And that is exactly where we are going today for this deep dive. I want you to run a thought experiment with me.
Okay, I'm ready.
Imagine you are standing on a sidewalk. It's a sunny day. You've got a high-speed camera in your hand.
Yeah.
And zooming past you, right down the center line of the street, is a rocket.
A rocket moving at, let's say, 99% of the speed of light.
Which is technically impossible for a standard rocket, but...
But we'll suspend our disbelief for a minute.
Right. The physics police can stand down.
Right.
We are in imagination land. So this rocket flies past, and you snap a photo exactly as it crosses in front of you.
Right.
The question is pretty simple. What does that photo actually look like?
Well, if you ask anyone who has taken a basic relativity course, or honestly even just watched a lot of sci-fi, they are going to give you a very specific answer. They'll say the rocket looks squashed.
Like a pancake.
Exactly, like an accordion that's been squeezed shut.
Okay.
This is called Lorentz contraction. The standard teaching is that objects moving near light speed get compressed in the direction they are traveling.
So a long rocket becomes a short, stubby disk.
That's the idea, yeah.
And that is the common knowledge. I mean, that's what I learned in school. Things get short when they go fast.
Right.
But, and this is exactly why we are here today, that is actually wrong.
Or at least, it's not the whole picture.
It is incomplete.
Yeah.
And it's been incomplete for a century. We just really haven't done a great job of talking about it.
No, we haven't. The real deep theoretical math has suggested for a long time that something much weirder happens.
Weirder than getting squashed flat.
Way weirder. If you took that photo, the rocket wouldn't just shrink. It would appear rotated.
Rotated? You mean like it actually turned sideways?
Exactly. Even though it is moving in a perfectly straight line to your camera, it would look like it had pivoted.
That's crazy.
You would see the side of the rocket, but you'd also see the back of the engines as if it were flying away from you at an angle.
That honestly feels like a glitch in the simulation.
Yeah.
How can something moving perfectly straight look like it's turning?
That is the mystery of the Tyrrell-Penrose effect.
Okay.
And for about 100 years, this was basically just a ghost story for physicists. It was lines of math on a chalkboard.
But that changed.
It did. This is the big news. In 2025, a team of researchers in Austria, specifically from TU Wien and the University of Vienna, finally managed to do the impossible.
They actually experimentally demonstrated this phenomenon.
They did.
They basically figured out how to photograph light speed geometry.
In a manner of speaking, yeah. They took the ghost story and turned it into a JPEG.
I love that.
Yeah.
So our mission for this deep dive is to unpack this. We need to figure out how on earth they did that.
Because they obviously didn't build a light-speed rocket.
Right. And we need to understand why a moving object looks rotated in the first place.
It really is a story about the lag time of reality.
A universe of delay. Let's start with the history, because you mentioned this idea is a century old. That takes us way back to the Roaring 20s.
1924, to be exact. We are in Vienna, and we have a physicist named Anton Lampe.
Wait, 1924, just a context check here. We barely had radio back then.
Let alone lasers or high-speed camera.
Quantum mechanics was basically a toddler. We had no supercomputers.
And yet here is Anton Lampe sitting at his desk at the University of Vienna thinking about the geometry of relativity.
Wow.
He was running that exact same thought experiment we just did with the rocket.
Just with pencil and paper?
Exactly. He realized that if a rod, just a simple stick, was moving at light speed, the light coming from different parts of that rod would behave in ways people weren't accounting for.
So does he publish this?
He does. He writes a paper about the appearance of a rod approaching the speed of light.
Okay.
He predicts that the visual shape would change in a way that wasn't just that simple contraction, but, and here's the tragic part, nobody really paid attention.
Why not? Was his math wrong?
No, his math was incredibly solid. but it was obscure, and quite frankly, it was so counterintuitive that it just didn't stick in the broader community.
Because the squashed idea was just easier.
Much easier. Lorentz contraction was easier to teach, easier to visualize. So Lampa's idea basically gathered dust for 35 years.
35 years. That is a long time in science. That's an entire career just gone.
It really is. It took until 1959 for it to resurface. That's when two real heavy hitters, Roger Penrose.
Who was a Nobel laureate, famously for his work on black holes.
Right. Roger Penrose and James Turrell independently rediscovered this. They looked at the equations and both went, wait a minute, we've been visualizing this all wrong.
And this is where we get the name Turrell-Penrose effect. Though, honestly, I feel like we should really be calling it the Lampa-Turrell-Penrose effect.
We probably should give Lampa his due, yeah.
Yeah.
But Penrose and Turrell were the ones who really formalized the visual rotation aspect of it.
How do they explain it?
They used the example of a cube.
Okay, let's have you visualize this cube with me. I've got a Rubik's Cube flying past me at Mach 1 million.
Very fast Rubik's Cube.
Standard physics says it looks like a flat square, right? Just the front face, smash flat.
Correct. That's the pancake view. But Penrose and Turrell argued that if you actually trace the individual light rays, you wouldn't see a flat square.
What would I see?
You would see the front face, sure, but you would also see the side face.
At the exact same time.
At the same time.
But wait, if you see the front and the side of a cube simultaneously, what does your brain tell you is happening?
That the cube is turned, it's rotated relative to me.
Bingo. It looks like the corner is pointing right at you.
Okay, I need to stop you there for a second. Because my brain is flat out rejecting this. That's normal.
The cube isn't actually rotating, it's moving straight. So why on earth am I seeing the side of it?
This is the hardest part to wrap your head around, so let's take it slow. It all comes down to the fact that light is fast, but it's not instant.
It has a travel time.
It has a travel time. Imagine that cube again. It has a front corner, the one closest to you as it approaches.
Right.
And it has a back corner, the one furthest away.
Got it.
Light has to physically travel from those corners to your eye for you to see them. The light from the back corner has to travel a longer distance to reach you than the light from the front corner.
Because it's literally further back. Okay, that makes perfect sense.
Right. Now, in our normal, slow, everyday life, that difference is tiny. We're talking nanoseconds.
Right, our brains don't process that.
It doesn't matter at all. But when the object is moving near the speed of light, the object moves a significant distance during the actual time that light is traveling.
Okay, let me try to construct an analogy here to make sure I'm getting this. It's like, imagine a rocket passing me.
A very fast rocket.
A warp speed rocket.
Yeah.
The light from the back thrusters takes longer to get to my eyes than the light from the nose cone.
Exactly.
So the image of the back of the rocket that I'm seeing is old.
Yes. You are seeing the back of the rocket as it was in the past, but you are seeing the nose cone as it is more recently.
So I'm seeing the back when the rocket was further away and the front when the rocket is closer to me.
Yes. And when your brain stitches those two things together, a far away back and a close up front, it stretches the visual image out.
Oh, wow.
It basically allows you to see around the corner. You are effectively peeking around the back of the object because that light left earlier when the object was in a position where the back was visible to your vantage point.
That is just wild. It's like looking at a star in the night sky. You're seeing the past.
Precisely.
But here, different parts of the exact same physical object are different amounts of past.
That is a perfect way to put it. You are looking at a single object, but you are seeing a smear of different time coordinates. And that smear constructs a geometry that looks exactly like rotation.
So Peter Schatzschneider, the lead author of this new study from TU Aiken, he calls it a trick of time.
It really is a trick. He specifically points out that this is not a mechanical distortion.
The cube isn't bending.
Right, the cube doesn't feel any different. If you were sitting on the cube, nothing is happening to you. It is purely a visual distortion caused by the lag of information arrival.
Okay, so that's the theory. 1924, 1959. The math definitively says rotation.
Yes.
But theory is one thing. Actually taking a picture of it in real life is another.
And that brings us to the present day, to the lab in Vienna.
I have to ask the obvious question here. How?
It's a fair question.
We can't accelerate a physical cube to light speed. I mean, we can barely get tiny subatomic particles to do that at places like CERN, and you can't exactly take a portrait of a proton.
No, you definitely can't. Protons are fuzzy quantum blobs. They don't have hard corners to rotate.
Right.
The team at TU Wien, led by Dominik Hornoff and Schatzschneider, They needed a macro object, something with a definite shape.
But they couldn't make it move that fast.
Exactly. So they decided to cheat.
I always love a good science hack. How do they cheat the speed of light?
They realized that since they couldn't physically change the speed of the object, they had to manipulate the timing of the camera instead. They simulated the delay.
Walk me through that. How do you simulate light delay?
They used a technique that they actually compared to the panorama mode on your iPhone. You know how that works, right?
Sure. I hold the phone, I sweep it slowly across the horizon, and the software stitches a bunch of thin vertical slices together to make one long photo.
Right. Now imagine you're taking a panorama of a moving car. If you sweep the camera in the exact same direction the car is moving, the car looks super stretched out. If you go the opposite way, it looks completely squashed.
Yeah, I've definitely seen those failed panorama photos online where a dog walks through the frame and looks like a centipede.
Exactly. That weird distortion happens because you are capturing different parts of the dog at different points in time.
Right.
The researchers essentially did a high-tech, highly controlled version of that. They didn't just take one quick photo of the object. They sliced the object into incredibly thin virtual segments.
Virtual slices.
Yes. They used a pulsed laser to illuminate the object. But here's the clever part. They didn't just shine a regular light on it. They used the laser to measure the actual flight time of the light.
Oh, like LiDAR.
Very similar concept. They projected patterns onto the object and used a very specific ultra-fast camera shutter. They synchronized the laser and the camera so that they were only capturing light that had traveled a highly specific distance.
So they were filtering the light by how long it had been flying.
Precisely. They could basically say, camera, only open for the light that reflects off the back corner.
Wow.
Then, camera, only open for the light that reflects off the front. By manually adjusting those delays, they could artificially create the exact lag that would happen if the object were moving at light speed.
That is incredibly smart. So they didn't need the object to move at all.
Not even a little bit.
They just needed to tell the camera, hey, pretend this light took an extra nanosecond to get here.
Yes. They effectively slowed the speed of light down to about 2 meters per second in their simulation.
That's practically walking speed.
Right. They turned a cosmic constant into a brisk walk so they could map it out perfectly. Schachtschneider compared it to taking nearly 150 million individual photos of the Grand Canyon and stitching them together to make one coherent sequence.
150 million. That is some serious data processing.
It was a massive undertaking, and to do it, they had to use something called blinding reflection or specular reflection.
What's that?
Well, usually when you take a photo, you hate glare. You want soft, diffuse light so you can see all the texture.
Right, glare ruins the shot.
Right.
Especially if you're taking a picture of something shiny.
But here, they actively needed the glare. They needed the light to bounce straight back into the camera lens to get a precise distance measurement. They were mapping the optical path length of every single point on that object's surface.
So they run this massive simulation, they scan the object, they stitch the 150 million data points together. What did the final picture actually look like?
They started with the cube, and when they rendered the image based on the relativity math,
Was it rotated?
it was rotated.
Just like Lampa predicted 100 years ago.
Perfectly. They saw the front face and they
Oh.
saw the side face, distorted exactly as the math said it should be.
That's incredible.
The pancake theory was officially dead. The visual rotation was real. And they published all of this in communications physics.
That must have been a huge champagne moment in the lab, proving a century-old ghost story completely true.
Oh, absolutely. But then they got a little cocky.
What did they do?
They decided to image a sphere.
A ball.
A sphere. Now, think about this for a second. If you rotate a perfectly smooth sphere, what does it look like?
It looks exactly like a sphere. I mean, a ball is a ball from any angle. The silhouette is just a circle.
Right. So when they applied the Terrell-Penrose effect to the sphere, the overall outline didn't change at all.
It didn't get squashed.
No, and rotating a circle visually doesn't change its shape.
Yeah.
So the ball remained a ball.
Okay, I have to be honest, that sounds a little underwhelming after the spinning cube.
Wait for it. The outline remained the same, but the surface details did not.
Okay.
Imagine a globe, like a map of the Earth.
Okay, I'm picturing a desktop globe.
When they simulated the light speed movement on that sphere, the map shifted. The team specifically noted in their findings that the North Pole is in a different place.
Whoa, hang on. The North Pole actually moved.
It appeared to move Because the top of the ball is further away from your eye than the middle of the ball, that same light lag effect kicks in.
Right.
The grid lines of the planet warped visually, the North Pole rotated downward toward the equator, and the backside of the sphere rotated into view.
That is the one that really breaks my brain.
It's hard to visualize.
Because with the cube, I can at least get the geometry. I can imagine seeing around a corner. But the idea that the North Pole, which is a fixed point, is just sliding around the surface based on how fast I'm going, that just feels inherently wrong.
It feels wrong because human intuition is built for slow speeds. We think of objects as solid, fixed things.
Right.
But this experiment perfectly shows that what we see is entirely dependent on the delivery system, the light itself. The North Pole isn't necessarily where you think it is, it's exactly where the light says it is at that specific moment.
So if I'm flying past Earth at light speed, Antarctica might genuinely look like it's on the equator.
Depending on your exact angle and speed, yes. The continents would squish and stretch and slide entirely around the surface. The map is not the territory, especially not at light speed.
This feels like it has major implications beyond just taking really cool photos.
Yeah.
I mean, does this matter for anything practical, or is it just physics fun?
Oh, it definitely matters for how we interpret actual data from the universe. We are constantly looking at things moving very fast out there. Jets from black holes, particles and accelerators.
So it changes our observations.
Right. This experimental setup, this slow-motion light camera they built, proves that we can actually simulate these extreme distortions right here in a lab.
So we can use this exact laser setup to study other relativistic weirdness.
Exactly. We can test complex theories about special relativity without having to actually build a starship to go see it. It turns abstract math into observable optics.
That's amazing.
It verifies that our fundamental understanding of the universe's rules is correct, even when those rules result in nonsense like a moving North Pole.
It really challenges the whole idea of objective reality, doesn't it?
It absolutely does. We tend to think that a photograph captures the truth.
Seeing is believing.
Right. But a photograph only captures the arrival of photons. And if those photons have different commute times, the quote-unquote truth gets completely distorted.
The truth is really just a matter of timing.
A universe of delay.
I really love that phrase. A universe of delay.
So we've gone from a sidewalk thought experiment to a laser lab in Vienna. We've learned that standard physics class kind of lied to us about the squashed rocket.
It was a well-intentioned lie.
Fair enough. And we've learned that at light speed, cubes, spin, and geography is completely fluid. It really makes you wonder, if speed changes the shape of a cube and the location of the North Pole to the person looking at it, is there a true shape of anything?
That is the big question.
Or is everything just relative to the observer?
Einstein would say the laws of physics are the exact same for everyone, but the measurements belong entirely to the observer. That is definitely something to stare at the ceiling and think about tonight. Before we wrap up, though, I saw the researchers had one piece of practical advice for us.
Oh, I saw that too. Very helpful stuff.
They said, if you ever do actually manage to travel at the speed of light, which, again, good luck,
Yeah.
remember that the camera adds 10 pounds.
And a whole lot of rotation.
Exactly. So you never really know which side of your face is going to show up in the picture.
So make sure you're looking good from every single angle, even the back of your head.
Sound advice for interstellar travel. Thanks for diving in with us today. Keep looking closely at the universe, and we'll see you next time.
See you then.